In this video, I'm going to show you how to integrate rational functions by a method of partial fractions. A rational function can be expressed as a sum of simpler fractions, which are called partial fractions. Finding these simpler fractions is the opposite of adding fractions over a common denominator. So for example, let's say I want to simplify this by joining these partial fractions together. So these are called partial fractions. So I'm going to get the common denominator, which is x, x minus 3, and x plus 2. So the first term needs to be multiplied by x minus 3 and x plus 2. The second term needs to be multiplied by x and x plus 2. And then the third term needs to be multiplied by x and x minus 3. And then all of this will be written over the common denominator of x times x minus 3 times x plus 2. So expanding, we're going to get negative x squared plus x plus 6 plus 5x squared plus 10x, and then plus 4x squared minus 12x, all over still the same common denominator. And then combining like terms in the numerator, I get 8x squared minus x and plus 6. All right, so taking these partial fractions and then adding them together, I get this new rational expression here. Now this means that 8x squared minus x plus 6 divided by x times x minus 3 times x plus 2 is equivalent to negative 1 divided by x plus 5 over x minus 3 plus 4 over x plus 2. That means that if I integrate the left side, with respect to x, it is the same as integrating the right side. And I can integrate each of these terms separately, or each of these partial fractions separately. Now you know how to integrate each of these partial fractions on the right side. So the method of partial fractions, it applies to integrals of the form p of x divided by q of x, where p of x and q of x are polynomials. Now the idea is to break the p of x divided by q of x into a sum of simpler fractions which are easier to integrate. Now the procedure is a bit long and it requires a lot of algebra. So therefore, before using partial fractions, you should be sure that there isn't an easier way to find the integral. Now, a couple of notes. If the rational function is proper, meaning the degree of the numerator, the p of x, is less than the degree of the q of x, then you can use the method of partial fractions immediately. However, if the rational function is improper, meaning the degree of p of x is greater than the degree of q of x, then you're going to need to use long division first until you obtain a remainder that has a lesser degree than q of x. Now I'm going to explain the method, and then afterwards I'll show you some examples because it definitely just need to practice. So let's consider an integral of the form p of x divided by q of x dx, where p of x and q of x are polynomials. So recall that the degree of a polynomial is the highest power of the variable that occurs in it. Now, if the degree of the top is greater than or equal to the degree of the bottom, then we need to divide the bottom into the top using long division. Now, step 2. Now that you've done this, if you need to, you will now have an integral that looks like p of x divided by q of x, where p of x and q of x are polynomials and then the numerator, the top, is smaller in degree than the bottom. Now that you have this, what we're going to do is we're going to factor the bottom of the fraction into a product of linear terms and irreducible quadratic terms. All right, what are those? A linear term is a term where the variable occurs only to the first power. So here are some linear terms: x minus 1, 2x minus 3, and x. An irreducible quadratic term is a quadratic term with only imaginary or complex roots. So that is, it is a quadratic which does not factor. So here are some irreducible quadratic terms: x squared plus 1, x squared minus 2x plus 5. Now you can check if the quadratic is irreducible by finding the discriminant. Remember, that's b squared minus 4ac, to determine the nature of the roots. And if you get a negative value, then we know that it's a complex number. So that means that the inside of the root, if you want to think of it in terms of the quadratic formula, is going to be negative. And then the quadratic doesn't factor. Now, a warning here actually. X squared minus 2 is not irreducible. So x squared minus 2 becomes x minus root 2 times x plus root 2. So ugly factors are allowed. X squared is also not considered an irreducible quadratic, since it is x minus 0 times x minus 0, which is the square of a linear term. So this distinction will become important in this next step. So this last step here is to obtain the partial fraction decomposition for the fraction. So this is the heart of the partial fractions method. It is basically a lot of algebra, but it's sufficiently complicated that the best way to describe it is simply by doing some examples. All right, so here's the first example. We're going to take this integral, which already has a smaller degree on the top compared to the bottom, and we are going to factor the denominator. So we get 5x minus 3 divided by x minus 3 and x plus 1 dx. So now I can separate this fraction into two parts. So we're going to say this is equal to a over x minus 3 plus b over x plus 1. So what we need to do now is to find out what a and b are. Multiplying through with by the common denominator of x minus 3 and x plus 1, I get 5x minus 3 equals a times x plus 1 plus b times x minus 3. All right, from here on, there are two ways or two methods to find a and b. So the first one is called, we're going to substitute x values into the right-hand side of the equation to make the terms drop out. So the right hand is the side containing a and b. So for example, let's say that x equals 3. If x equals 3, we can see that b would be multiplied by 0 here, and this would no longer be part of the equation. So then we would only have to solve for a. So plugging in x equals 3, we get 5 times 3 minus 3 equals to a times 3 plus 1. So we get 12 equals to 4a, and then a equals 3. We can do something similarly to find b. So this time we're going to make x in this equation here equal to negative 1. So that the a is going to be multiplied by 0, and then that will drop out. So now we have 5 times negative 1 minus 3 equals b times negative 1 minus 3. So now we have negative 8 equals to negative 4 times b, and b is equal to 2. So this is great. So now I know a is 3 and b is 2. I'm going to substitute it back into this equation here. So we have the integral of 5x minus 3 divided by x minus 3 times x plus 1 dx equaling to the integral of 3 divided by x minus 3 dx plus the integral of 2 divided by x plus 1 dx. And that's going to equal 3 times, and then the integral of x minus 3 is the natural log of the absolute value of x minus 3 plus 2 times the natural log of x plus 1, and then plus c. Now the second method is called equating coefficients, and it requires us to multiply out the right side and collect like powers of x. So I'm going to proceed by multiplying out my right side. So let me just recopy this out first. A times x plus 1 plus b times x minus 3. So we're going to multiply the right side. And then what we're going to do is we're going to rearrange them by collecting all the terms that contain an x and placing it first. And if it doesn't have an x, we're going to place it second. So now I'm going to factor out an x from the first two terms. So I have a plus b times x plus a minus 3b. All right, so equating coefficients means that a plus b, which is in front of x, should be equal to 5. And I also have that negative 3 is a constant, which should be equal to the constants here, which contain no x. So we have negative 3 equals to a minus 3b. So now what we have is a system of equations. And these are not lined up nicely. I'm going to subtract. So 5 minus negative 3 is 8 equals to a minus a is 0. B minus negative 3b is 4 times b. So b is equal to 2. So now that we know b is 2, we can plug this back into this red equation I have. So 5 equals a plus 2. So a equals 3. Now I'm going to stop here because we can actually just go back to what we did back here and substitute a equals 3 and b equals 2 into the partial fractions above. So substitute a equals 3 and b equals 2 into the partial fractions like above, and then integrate. Okay, so to identify a little bit of sections here, so this is where we are equating coefficients. So equate our coefficients at this step. And then in this step here, we are solving the system of equations. Sometimes you might have more variables, which we'll see later on, and you might have 3 or 4 or even 5 different variables, but then you will have 3, 4, or 5 equations as well.